Now this one, I like this one as well because previously, if you may have run into this, if you're doing 3-axis horizontal finishing, um, you didn't always have exact control over the distance between the cut levels. Correct me if I'm wrong, Joe. It calculated the overall distance and then overall cut depth, and then divided that by the maximum distance, and then it would fluctuate in between that. And I know I
Oh,
probably messed that up a little bit, Joe. Go ahead.
yeah. So what the system was doing before was using the step-down control distance and computing integral number of cuts between the top and the bottom Z levels. So you would always get a cut at the top, and you would always get a cut at the bottom. And this way, and you would get, obviously, it's integral number of cuts, so to ensure that you would get a cut at the top, at the bottom. And since this requirement actually forced the system to recompute the actual step-down distance to be slightly smaller in many cases than the actually specified distance. Some users, what they wanted is they didn't want the system to actually change that distance at all. They wanted these cut levels to be exactly as they specified. And in the 2024 version, you can do that, but the problem with that, obviously, is you will not get a cut level at the bottommost cut. So, that's the trade-off here. So, but in some situations, the exact cut levels are important to customers, so that's why we added this enhancement.
Yeah, and also just look at these two images. The one on the right is in version 23, where the cut levels didn't fall exactly at the depth that the user specified. In this case, which is a distance of 1 millimeter. If you look at this example part, it's just a stack, topographical stack of surfaces at 1 millimeter intervals. So now you can actually set the distance at 1 and check this box here, and it'll maintain exactly that distance, as you can see over here under the 2024 image right here. Now this is one that goes to my heart specifically, because I've always felt that we needed better contact conditions for mold makers, specifically around the parting lines. And in version 23, the default condition was the on condition, meaning that I'm going to show this a little bit better in the part file demo, but in the on condition, the tool axis in the tip of the tool, when it aligned itself with the perimeter curve that you're machining, it would stop. And for cavity, parts that have cavities, the tool is actually rolling up over the parting line, which is a big no-no. Tool makers do not like to see that tool ride that parting line. So in 24, we added a new condition called the contact. So whenever the tip, for example, if you're using a ball mill, whenever the machining ball of the tool makes contact with that perimeter edge of the surface, it stops. And then starts going, in the reverse direction, or where it's supposed to go, opposite that direction. So just if you look in these simulations, you'll see that down below in previous versions, the tool was riding up on the parting line and actually messing up the parting line. And you would see that in your actual molded parts, which is not good. So on top, we see the 2024 contact condition, nice, clean cut around the parting line. Previously, in order to get that, we actually added masking surfaces or guide surfaces to help guide the tool past the parting line. Now you don't have to do that for a specific set of cavities. So I'm going to show this as well. Tool contact condition. So what I've got here, I got two identical cavities, okay? And I've got operations up here. In previous versions, if you wanted to machine this cavity, the default position for the tool was the on condition. Whether you used the containment regions tab or the part surfaces tab, the default was on. You only had on, to, and past. Well, what happens with that is you didn't have any options to control that tool at the actual parting line. So in this case, when I do the simulation, you'll see it, the tool starts actually ramping up over the parting line, which is pretty bad. So in the, we've added a new condition called contact, where the tool stops when any portion of the machining ball of the tool makes contact with the surface perimeter curve or edge, it will stop. So let's, to get a good idea of that, let's go ahead and simulate this real quick. So I'm going to do simulate this. Sorry about that. Okay, let's change this to mop. Turn the toolpath off. So there's our roughing. Let's go ahead and make some changes here to the stock. Let's turn these off. Let's turn this to that. Click OK. Okay, so there's our horizontal roughing operation. So previously, and this is the first parallel finishing where we just had the default on condition. Okay, and let's go ahead and simulate that. Okay, well that's just to clear it, so that's not the actual cavity. So let's do the cavity here. So this is the default on condition based on the cavity, which is selected as the control geometry, and the perimeter of the cavity is actually the parting line. So you can really get an idea of how the parting line is violated based on the tool, the axis of the tool aligning itself on the perimeter of the cavity. And as you can see, the tool rides up over the cavity, and this is all flash in the actual part. If you molded this part, you would see flash in these areas because that parting line was violated. Okay, so let's go ahead and look at the part on the right with the contact surface condition. Select the two surfaces. The contact is set to the surface extend condition is set to contact. Let's go ahead and simulate that. So now you can really appreciate this simulation. I mean, no violation of the parting line. Let's go ahead and go to the multi-viewport.
I just want to clarify a little bit, Don. The choice of words violation might be a little harsh because.
Well, when you're a tool maker, that's a violation because I mean.
Well, I want to, from a system perspective, I want to say in the previous operation, the system is maintaining everything within tolerance. So even though it's riding that edge, everything is within tolerance. But when you actually machine, when the tool is actually touching it, yeah, you're going to have some sort of blemishes in the part, which is what Don is terming violation, that I'm taking objection to. So anyway, thanks.
Okay, well, just a clarification there. Joe mentioned that everything is within tolerance. The problem with that is when a tool touches the parting line more than once, a tolerance is applied. So if you're applying a tolerance when it touches the first time, then you're applying a tolerance that touches the second time. That's a tolerance stack, which can come out to be a violation or undercut or an overcut of the actual parting line. So if you're contacting more than twice, you can just imagine you're just going back over that parting line, going back over the parting line, the same point on the parting line, it degrades the parting line. So that's why if you see pictures of molded parts, this happens a lot in prototype parts where you're not really trying to be exact, just for the prototype. You'll see a lot of flashing, you'll see mismatching of the parting line, and all that's because the tool had its way with the parting line when it cut. And that's a big no-no in cutting cavities for mold making. So what I was going to do here is I was just going to show you Let's turn the path on, and let's change this to, just do it to the wireframe, okay? And let's just run that tool. Let's just run it down there. Okay, so let's go back over to the very, okay, so let's go on down where it, right towards the middle. Okay, that's pretty close. So you'll see that right there, the ball of the tool made contact, or pretty close, made contact to the perimeter of the surface, the actual cavity, and that is the parting line. So once it touches that parting line, the tool stops and reverses in the other direction. That's why you see that it's not really covering all of the cavity, but in fact it is. The path is only calculated based on the tip of the tool, but that entire cavity is being machined very precisely and not going over that parting line back and forth as it was in the on condition. Now, we also have another part lined up for this, which shows this as well. You may have seen this mold cavity. We use that in a lot of different cases to show different things. Well, if you look at this cavity, you have a lot of contoured surfaces in the cavity itself. And with the on condition, you'll see that the tool actually rides all the way up. Let's go to here. You'll see that the tool is riding all the way up. Any of this arc, you see this arcing motion right here? That's where the tool is riding on a specific surface edge. So if we go to the contact condition, you'll see that it doesn't ride. When that tool comes up and it touches that surface perimeter curve, it will stop and then reverse in the other direction. Now in this case, this is not the actual parting line. It's calculated based on the edge of this fillet. But even so, you could be doing this fillet with a different operation, and this may be a critical area on the mold itself. So you don't want that tool, to constantly ride that edge. So now you have very precise control over the tool at the perimeter of the surface, which is in fact the parting line. So that's, I don't want to underestimate this enough or overestimate this enough, because this is really a big deal for mold makers. So if you got any mold makers that are watching, you understand how important this is. So let's say we put about 10 minutes on that one. We're having pretty good on time. So if you guys got any questions, go ahead and put them in the questions bar. And it looks like we're going to have time at the end to cover those. So what are we going to do? We're going to talk about another 3-axis enhancement, calling it exact Z-level distances. And let's take a look at. So this was the cut transfer method where we mentioned let's go into this and look at the actual clearance plane. So in the clearance plane definition, we have the clearance plane definition set to automatic, and then we have the cut transfer method set to skim. Well, as we discussed in the slide previously, when you set it to skim, the skim was calculated based on the maximum extents of the part in the Z level. So the tool was always retracting up a little bit past the part based on the skim clearance. Well, that is some wasted moves if you're machining in an area that doesn't transverse across the part. So let's go ahead and take a look at some of these look at this by cut levels here. So we're going to just work our way down. You'll see in the, at the top level, pretty much everything is based on the cut level of the in-process stock, basically. But as you get down deeper, you'll see that the clearance, the retract clearance gets larger, or more distance, higher up, I should say. It's always clearing the top of the part. Well, now if we go down in some of these other cut levels, you'll see over here, it didn't need to go all the way up past the part, so the skim clearance was applied based on the in-process stock, which is the cut level, this cut level right here. So it extended up, skimmed the top of the cut level, okay? And you'll see that a lot in some other cases. Here's another, you'll see these here. No need to extend all the way up past the part in these types of conditions. So you can imagine if this is a relatively simple part, a very complex part, you could virtually save minutes, if not more, in the machining time by not having to retract and transfer all the way up to the skim clearance above the part. Okay, let's look at some 4-axis enhancements here. So what we're going to look at here